Uh, Hi, good evening, everyone. My name is Chetan Singh Chauhan. I'm the Secretary of Kaziranga House. We have here um, one of our sessions. We have planned an entire series of sessions for the end term exam. We have sent out an email for that at 6 o'clock today in the evening. So you can take a look at that and see what other sessions which we have planned, and you can join those too. So this is the second session of that series, a week-long series that we have planned for all of you. This is the second session for the series for Maths-2 revision session. So please welcome Detective Dipanshu Singh Best. He was the previous Maths. He was previously the Maths-2 TA for the data science degree. So and currently he's the TA for Maths 2 for electronic systems. So please welcome Dipanshu Singh Best. Dipanshu, are you there?
Hi, hello.
Yeah, please take and welcome
Okay,
to the session.
thank you so much. I'll just start presenting my screen. Just let me know if it is visible. Share. Here we go.
Yeah, perfectly visible.
Okay, it's visible. So in today's session, what we'll be doing is we'll just go through our latest PYQ. Uh, it has around 40 questions, so it will cover most of the topics which are important for your exams. If you want to know about the weightage, it's like 50% for from your week 9 to 12. Then rest of the 35% will be from your week 5 to your week 8, and then rest of the weightage will be from your first 4 weeks. So let's start by solving the questions. Here, the very first question that we see is asking us that we are given a set and the set is linearly dependent. So how to check whether a set is a linearly dependent set? So basically it means that one of the vector can be represented as a linear combination of other two vectors if a set of three vectors is given. So here it is given to us that the set is linearly dependent. So if you remember, if we arrange these vectors as the rows or as the columns of my matrix, so what I know from the properties of determinant is that if the rows are linearly dependent, or maybe if the columns are linearly dependent, in that case, the determinant of the matrix becomes zero. So I'll be using the same property here. I have arranged the given vectors as the rows. If you want, you can arrange them as columns as well. And what we are going to do here is we'll just say the determinant of this matrix is equal to zero. So that would give us the value of alpha. Here I have written A, but it's alpha. Okay, just for the simplicity. So you solve this determinant, I guess we are very well versed with that. 1 times of this small determinant here, and then this minus a times of very just a second. This should be my first row, and we'll equate it to 0 again. 2a minus of a square minus of a times of this is plus 3, I guess, equal to 0. Just pardon if there are any calculation mistakes, but what we got from here is minus a square. 2a minus 3a is minus a equal to 0. That gives you a equal to 0 is one of the answers, and the second one would be maybe a equal to minus 1. Are we correct, or have we made any calculation mistake? So just give me a second to check on that. Mm, this times of 2a minus of a square, this becomes plus of a square, sorry, my bad. And then a times of 0 3 minus 1a, and then 0 times of this. Oh, sorry, this should be minus a here, 3a square a. Few things will change. You just need to fix it. I guess here it is a, and what else? Something will change from here as well. No. Yes. This a will change. Fine. So here we have 2a minus of plus of a cube, sorry. And from here we get a times of 3a. That gives us a cube minus of 3a square plus 2a equal to 0. And from here we get a equal to 0 as one of the answers. I'll just simplify it a bit. A square minus 3a plus 2 equal to 0. Guys, you can please unmute yourself and just answer some of these calculation parts at least. So this should be minus 2 and here it will be minus 1, I guess, equal to 0, a equal to 0, 1, 2. So these are three permissible values for your a. This option C. Okay, are there any questions, doubts? Hello?
Guys, just one thing. So before, I mean, the session is going to continue for 1.5 hour at least, if not 2 hours. Okay. Just a small request from my side. Just unmute yourself and interact with the Panchu. So it will not be a one-sided session. I want it to be an interactive one. You can respond. Doesn't matter whether you have prepared for the end term or not. We assume that you're still in preparation or you have just started. That is the reason why we are even conducting the session. So no need to feel hesitant. Doesn't matter. We are not going to ask you here what is the level of preparation you have. We are here to just help you out. So just unmute yourself, interact, ask any doubts. You don't have any doubts, you don't understand anything, just say it. I don't understand. मेरे को समझ ही नहीं आया. I don't even understand. So yeah, just interact. Yeah, Pallavi.
Yeah, I was asking for linear dependence and independence one more time.
Sure. So your linear dependence means that the vectors that you have are dependent on each other or can be represented as a linear combination of other vectors. I'll give you an example here. So suppose you have a vector v1. Okay, v1 is 1 comma 0, v2 is 2, let's say 0 comma 1, and your v3 is some 2 comma 3. So if I give you this set of v1, v2, v3, is this set dependent or independent? So what I do here is, see, this v3 could be represented as 2 times of v1 plus 3 times of v2, right? Because 1 will give you this 2 comma 3. So that means these three vectors are linearly dependent. Okay, they are not independent of each other. Okay, but what if I just remove this v3 guy from the set? Okay, so I'm going to take a new set here. Let's call it T, which only contains v1 and v2. Now, what we know about these v1 and v2 are that they cannot be represented as a linear. One cannot be represented as a linear combination of other. Right? I cannot represent my v1 as some constant times of v2. Okay. Now this means that this set T here is a linearly independent set.
Okay, got it.
Dependence and independence means. I hope it is fine. Where in the meeting tab is? I can't find it. No issues. Am I there in the meeting? I hope
Yeah,
I'm
you
there.
are there in the.
Yes,
Yes.
yes.
Okay. Uh, fine. So moving on
Sorry
to
to
the
interrupt.
next
This
question.
recorded link will be available in the calendar, right? So if you want
So
to,
this is a session conducted by Kaziranga House. You can
okay,
find the session recording on the YouTube channel of Kaziranga House.
okay. So we cannot find. So if you want to refer, maybe after that, na, so how we can see?
Yeah, you can go to the YouTube channel and you can see the video.
Okay, okay.
Okay. Coming back to our question, here we have a function defined on, see, this is your domain. This means that entire R2 space, but that does not contain the 0, comma 0 point, does not contain origin. And if you look at the options, you will get the idea why, because if you take your x and y as 0, your denominator everywhere will become 0. So this is not permissible for your domain. That is why we are taking this domain where the entire R2 space is there except the point 0 comma 0. So now for these four functions we need to check whether the limit exists at the point 0 comma 0 or not. So for a multivariable function, how do we check whether a limit exists for a specific point or not? The idea is very simple. We just take a curve and we check whether the limit exists along that curve or not. Okay, I'll just explain it with the help of an example. For example, we take the very first problem given to us, that is f1 of xy. I'm just writing it f1 once. For rest of the time, I'll just write it as f. Okay, it is given as x square plus y square sine of 1 over x square plus y square, and I just need to check whether the limit exists at the point 0 comma 0 or not. So what we do in such situations is we maybe take a curve. So here we are going to take this curve. Uh, our curve along which we'll check is y equal to x. For most of the cases, this y equal to x will do the job for you. Okay, so if you see the powers of x and y are same everywhere, wherever x square is present, y square is also present. It's kind of very symmetric structure, then this y equal to x curve should do the task for you. Now, what does this curve mean? So this curve means what we are going to do here is we'll take a point 1 comma n and 1 comma n. Now why this point 1 comma n 1 comma n? So the idea here is as the n tend towards infinity, or maybe this one, sorry, infi inf ty infinity, this 1 by n comma 1 by n will tend towards 0 comma 0, and this is the point where we have to check the limit, right? Limit means what? As we will move towards that point, towards a space along a specific curve, the value of the function will also tends toward a fixed number, will converge towards a fixed real number. Okay, so what happens here? What we will do is we'll try to find limit of my 1 comma n 1 comma n going to, or maybe in easy words I can write it as my limit of n going to infinity such that f of 1 comma n 1 by n comma 1 by n. Okay, so it's like an algorithm that you can keep in your mind and it will help you to solve the problem. Okay, so you take this point 1 by n comma 1 by n. As you take your n towards the infinity, your point tends towards 0 comma 0. So here in place of x and y, we are going to substitute this 1 comma n and 1 comma n, and we'll take our n towards the infinity. Let's see what happens if we do the same thing for this function. Here we see my, instead of x square, I'll have my 1 by n whole square. Okay, so it can be written as 1 by n square. I'll just remove this guy from here. Same goes with this y square. Now here you see this is a very simplified version of y, and in place of y, it becomes 1 by n square. So now what happens as your n goes towards the infinity? Here you have sine, and 1 by n square plus 1 by n square gives you 2 by n square. So 1 over 2 by n square means here we have written n square by 2. Okay, and we need not to forget writing this limit n tends to infinity. Now here you see this is a very simplified version of this limit. Now if you notice, as n will tend towards infinity, this n square by 2 will also tend towards infinity, right? So this eventually means sine infinity. Now the value of sine will oscillate between -1 to 1 because we do not know the exact value of sine infinity. That is why the limit does not exist for the first function at the point 0 comma 0, right? Because this limit here does not exist. Fine. Now can you do the same thing for the next function out there? Okay. So the only difference in the next function is everything is kind of same. Okay. Just here you put 2 and you multiply your value of sine of 1 over x square plus y square by x square plus y square. Now what happens if you just make this very slight change? Here, when you substitute the value of your x and y as 1 comma n and 1 comma n, 1 by n and 1 by n, you get 1 by n square plus 1 by n square times this. Okay, and this is nothing but, let me write it as 2 by n square, and the same thing here could be written as just a second, 1 over 1 by n square, not 1, 2 by n square, because this is 1 by n square plus 1 by n square, right? So if you just look at this, as n goes towards the infinity, this guy tends towards 0. So if you remember, this is equivalent to this limit over here. So I have a limit of, maybe let's say my a going to 0, a going to 0, such that it is some 0 times of, let's say, sine, and here it is, let's say, my a and a. Okay, this is a much simplified version of this. Are there any questions till here? Like, if you can see from here itself, this step is completely optional. But let's say you want to simplify it and write it here. This is also one of the way you can represent it. Now, is there any question till here? How we came from here to here? Hello, am I in the meet?
Guys, please respond to the point. As I said,
Can you
we
please
will not be able
explain
to.
that again?
Uh, exactly which part from here?
Yeah.
Okay. See, if your n tend towards the infinity, what happens to this guy?
Mm, see, it tends towards zero.
Yes. That is why we have written a over here. This is some n entity that tends towards zero. And this is the same entity, right? So this A will also tends towards zero. And that is why we have written that limit of A tends towards zero. This A will tend towards zero and this A will also tends towards zero. Now the point here is that what will be the answer of this limit? Or maybe if you do not want to write this step from here also, if you could see what will be the answer of this limit. So earlier our problem was that this part was unknown. Okay, I do not know what happens if I have sine 1 over 0 over 1 divided by 0. That is, I do not know what happens if I have sine infinity over here. I do not know the exact value of sine infinity. But what I know about sine infinity is that it is going to be some number between -1 and +1, right? But for sure, I know about this entity that this entity is going to tend towards 0. So 0 times of something that will lie between -1 and +1, right? So it is eventually 0 times of some number, which will mean the product will be equal to 0, right? So either you skip this step or you just write your answer from here. In both the cases, you're going to get your answer as 0.
Sir, is there
Are there
any
any
other, sir,
questions?
is there any other way to do this type of questions?
Any other way of doing these type of questions? Sorry, but this is the most simplest approach that you'll find solve any kind of limit. So to solve the limit, you'll have to pick a direction. Okay, and then you move along that curve. The second way is we have second way as well. It's not like that it is the only way. For example, what we are putting here totally depends on the curve that we are choosing. Okay, let's suppose we choose uh, x-axis as the curve. Okay, for the same question, curve is x-axis means your y is going to be 0. So if your y is going to be 0, then what you do is you say for some n going to n tending to infinity, my let's say 1 by n comma 0 will tend towards 0 comma 0. So you see with this curve, the value of y is always going to be 0. So it will be, let's say, slightly easy for you. Instead of 2 by n square, maybe you will get 1 by n square. But eventually, you'll reach to the stage where this number will tend towards 0 and this will be some number between -1 and 1, and their product will tend towards 0. Okay, so if
Yes, sir.
you just copy all these steps from here, paste it here. So the only difference that you will get is this maybe. Okay, the idea for the limits is no matter what curve you choose. Okay, if for all curves you are reaching to the same value, then your limit exists.
Sir,
Because
how
there
to
could be
choose the
cases, let's
curve?
suppose I chose this curve and then I chose
Hello.
some other curve, and for both the curves I'm getting two different answers for my limit. Then in that case, it would mean that the limit does not exist. See, for a single variable function, it is very simple, right? Because it's a line. So in a line, there are only two ways of approaching. Either you approach from the left or you approach from the right. That is why we say left hand limit, right hand limit. But when we talk about two-dimensional space, for a single point, to a single point, there are infinite number of curves through which I can reach to that point. Okay, and we have chosen the simplest of the curves so that the calculation becomes simple for us. Okay, but no matter what curve you choose, you're always going to get the same answer if the limit exists at that point. Okay, similarly, Similarly, I guess you can do rest of the options as
Sorry,
well. Here
sorry,
also, if you
sorry to
uh,
interrupt. Question for just could you please
mhm.
explain because is R2 less 00 means what is actually so uh, so
Oh, this.
yeah,
Yes, so we started our question from here only. This means the function is defined on this domain. This is the domain that your function can take all the values of R2 except 0, comma 0. Why 0,
okay,
comma 0 is prohibited? Because you see, if I put 0, comma 0, then this function will
infinity.
not give me the, yeah, this function will not take the value 0, comma 0. Right, so I can say that yes, the limiting value is there as I move towards 0, comma 0 for this function, but exactly at the point 0, comma 0, this function does not give me any meaningful value.
Okay,
Okay, that is why 0, comma 0 is not included in the domain because the value of the function does not exist at that point. Okay, so what I was saying is similarly you can do for your f3 and f4. So you just start with, let's say you take the curve y equal to 0. So in place of x, you put 1 by n. In place of y, you just put 0 and you take your n towards the infinity. So your 1 by n will tend towards 0. So this will be sine of 1 by n square divided by 1 by n square. So again, you get something of the form sine 0 by 0. That gives you 1. So limit exists for this guy as well. And the answer here would be 1, I guess. But for f4, if you take x as 1 by n and y as 0, you see what you are getting here. You are getting um, 1 by n square divided by 1 by n square sine 1. So if you approach along the x-axis, that is by taking y equal to 0, you get sine 1 as the limit. But if you see, there is not complete symmetry. It is minus of y square. So if you approach along the y-axis, that is you take x equal to 0 and you take y equal to 1 by n, then in that case, this will be 0 minus 1 by n square divided by 0 plus 1 by n square. That will be equal to sine of minus 1. So you see, if you approach along the y-axis, you are getting the limit as sine of minus 1, which is equal to minus of sine of 1. And when we were approaching along the x-axis by taking y equal to 0, we were getting the limit as sine of 1. So for two different curves, we are getting two different values for the limit. That would mean that the limit does not exist for this function at 0, comma 0. Okay, so only B and C should be the correct answer. Are there any doubts? Like I just quickly went through it.
so it should come zero. That is only the correct answer, right?
Sorry, could you repeat again, please?
So when substituting the limits, it should come zero.
No, 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 no. By substituting the limit, you should get any real number value as your answer or any scalar as your answer.
Okay,
Okay,
okay.
because we are not dealing with the complex function, so mostly we'll get real numbers. But in general, you can say your answer should be any scalar.
But third and
Okay.
fourth, you just you told something, right? So third and fourth.
Third, it exists. Third, it exists because the limit that you're getting here is 1.
Okay.
But
Fourth.
fourth, the problem with fourth is if you approach along the x-axis, that means y equal to 0, you are getting sine of 1 as the limit. Okay, I'll
Okay.
just do it here. Just give me a second. We are going to do part D now. Yes, this part is important, so maybe we can spend some time here. Not an issue. So for us, f4 of x comma y is given as sine of x square minus of y square square plus of y square. So you see here one thing that it is not totally symmetrical, right? Because if you put y in place of x, you get y square minus x square, which is not same as x square minus y square. That gives us a hint that maybe we should check for more curves, not a single curve. Okay, for any other option, you'll see the x and y are pretty much symmetrical. So only one curve would suffice. So here we'll be checking across two curves. First is, let's say, along the curve y equal to 0, which is your x-axis. So if we check along the x-axis what we are getting, we say as my n tends towards infinity, my 1 by n comma 0 will tend towards 0 comma 0. Okay, the curve is any x comma 0 because this will always lie on my x-axis. Now, so if I take my limit here, limit of n tending to uh, infinity, let's say, of f(x, y), that is 1 by n comma 0. This this will mean what? That here I have 1 by n square, and here also I have the same thing. Yes, here also I have the same thing with limit of n tending towards infinity. But you see, here I get a constant as my answer, and the constant is sine of 1. Again, this is a scalar quantity. So we are good to go. But we'll also check along the curve x equal to 0, or maybe you can say your y-axis. Along the curve x equal to 0. Why? Just because we do not feel the symmetry here. What will be the difference? Maybe we can copy the same thing from here, paste here, but this time it will be 0 comma 1 by n, not 1 by n comma 0, because this point will lie on y-axis. Again, here it should be 0 comma 1 by n. And here, if you see, if I substitute 1 by n in place of y and 0 in place of x, I get minus of minus of 1 by n square in my numerator. So that gives me sine of minus 1, or maybe minus of sine of 1. So from here, I can say that the limit that I got along the curve y equal to 0 is not equal to the limit that I got along the curve x equal to 0. That is why limit does not exist. Okay, for a limit to exist, it should give me the same value along any curve that I choose. I hope it is clear now.
Got it. Got it. Thank you.
Yes.
But why we are always using 1 by n actually? Is there any specific reason? But the points you are taking x and y, so 1 by n you are taking, right? So
Just a standard practice. You can also take x tending to 0 and x comma 0.
okay,
Also works. Just a
okay,
standard practice that we follow.
okay, okay. Thank you.
Hmm. The next is which of the following sequences in R2 are convergent. So to check whether they are convergent, whether the sequence is convergent or not, you just say what happens to this sequence as I take my n towards the infinity. So you see, for the first option, as n approaches infinity, what happens to the numerator here? Cos infinity. So cos infinity will again be some number between minus 1 and 1. But what happens to the denominator? Denominator will be infinity. Okay, so this number here in the numerator will oscillate between minus 1 and 1, but the denominator will keep increasing as I take my n towards the infinity. So as n approaches infinity, the first term here becomes 0, and same happens to the second term. 1 by n also approaches 0 as n approaches infinity. So yes, the value is converging to 0 comma 0 as n approaches infinity. So the first guy over here is convergent, or the first series here is convergent. Fine. Any questions? Okay,
Yes,
no
sir.
questions. Fine.
Sir,
What
why,
happens to the second series? Yes.
sir, why cos n, how
Mhm.
cos infinity oscillates between -1 to 1?
Have you seen the graph of cos theta? If I just draw here, okay, just to show you, we'll plot a function of y equal to cos x. Okay, just or maybe let's do it like this. So if you see the graph of y equal to cos x, done. Here, this is an oscillatory curve. Same happens with y equal to sin x. The only difference, it starts from here and goes like this. So it's an oscillatory curve, and no matter what argument you choose for your theta, the value of cos is always going to stay between these two boundaries, -1 and 1. So we say such kind of graphs are bounded. They're bounded by the boundaries of -1 and 1. So no matter what value you choose for your argument, again, it cannot exceed 1 and it cannot go below -1. So again, we do not know the exact value of infinity, but yes, whatever it is, the value of cos will not exceed 1 or will not go below -1. Again, I'm repeating the same point, but yes. Okay, so there is going to be some number between -1 and 1. Okay, yes.
Can you please explain this convergent concept one time? I just got confused.
Convergent means as n approaches infinity, as the sequence approaches its infinite term. Okay, because it is what? It is for you, maybe if I just write the sequence n, I'll just erase it. This would mean I'm talking about maybe start with 1, 2, 3, 4, 5, 6, 7, 8, and so on. So such type of series sequences are called divergent sequences. Why divergent? Because you see, as n is approaching infinity, there is no specific value that I am approaching. Okay, as n approaches infinity, here the sequence will keep growing. So this is divergent. But if I take, let's say, uh, 1 by n, what happens if I take 1 by n? Uh, Sorry. Hmm. What happens if I take 1 by n? This would mean that I'm starting by 1 maybe, then 1 by 2, 1 by 3, and so on. So if you notice here, as the value of n keeps increasing, the value of this fraction is decreasing. It is 1, 0.5, 0.33, then 0.25, then 0.2, and so on. So this is convergent, as because the value of n approaches towards infinity, the values of this fraction goes towards zero and towards zero. So the value is approaching a specific point. That is why I call such sequences or series as convergent sequences. Okay, I hope that this
Yeah, got it.
clears your doubt. So what happens here as n approaches infinity, 1 by n approaches 0. So e power 0 again is 1. So as n approaches infinity, the first term over here approaches 1, which is again a known value. What happens to the second guy? As n approaches infinity, this e of infinity also approaches infinity, but because it's present in the denominator, 1 over infinity becomes 0. So what I know here is as n approaches infinity, this sequence approaches 1 comma 0, which is a point. Again, a point. That means the sequence is convergent because I'm getting a known point here. So first two sequences are convergent, but let's take this as an example. As n goes towards the infinity, this this n will also move towards infinity. So infinity multiplied by, see, doesn't matter what this is. This is cos of 0. Cos of 0 is what? Cos 0 is 1. So infinity times 1 gives you what? Infinity, right? So as you can see, the very first term itself is not approaching any specific value. It's also going towards infinity. So we'll say no, this is not a convergent sequence. And what about this one? So here, if you notice, the second one approaches 0 because sine of n will stay between -1 and 1. But as the denominator approaches infinity, the overall term becomes 0. But here, -1 to the power infinity. Now we do not know exactly whether infinity is an even number or whether it is an odd number. So we will not be able to know whether this -1 to the power n is going to be +1 or -1. It's not a fixed value because again, as the value of n will change, this value will keep changing as well. So yes, because of the first term over here, this fourth option is also not a convergent sequence. So only first two options are convergent. Hope that clears your doubt as well.
Yes, sir.
Hmm. Moving on to the next option where next question where we have to check which all options are true. So if you see, first it says if B is a linear combination of the columns of the coefficient matrix A, then the system of linear equations AX equal to B has a solution. So you see, whenever you are given a system of linear equation, let's denote it by AX equal to B, the solution exists if and only if this guy B, or what we call as the known vector, lies in the column space of this coefficient matrix A. Lying in the column space means B can be represented as some linear combination of columns of A. Okay. Why? Because the term written on the left hand side itself means linear combination of the columns of A. AX means that linear combination of columns of A. Why? Because if let's say my x is some x comma y comma z, that would mean x times of first column plus y times of second column plus z times of third column, etc. Okay.
When
So
you
what the
say like
question says,
there is unique or
mhm,
infinite solution, like how will you decide for Ax equal to B?
how will you decide whether the solution is unique or not? Hmm.
Yeah.
Uh, for that, first, let's say you know that B lies in the column space of A. Then there are two possibilities. Either your you have a unique solution or you have infinitely many solutions. So in such cases, if the determinant of A is non-zero, then you get a unique solution. Okay, so to get a unique solution, you should have the determinant of A as some non-zero value. Okay, because how do you know that? Because let's say determinant of A is non-zero. That would mean that A is invertible. Okay, and if A is invertible, then it means A inverse exists. So I can pre-multiply both sides by A inverse. That will give me A inverse times of A becomes I times of X becomes X only. And here I get A inverse of B. So in this case, I'm getting a singular solution for my X if the determinant of A is non-zero. But if the determinant of A, let's say the determinant is not defined for A because it's not necessary for it to be a square matrix. Or let's say even if it is a square matrix, then the determinant of A is zero and B lies in the column space of A. In that case, it has infinitely many solutions.
No, like I'm not getting for rectangular matrix. How will you decide if it is invertible or not? If A is rectangular,
Yeah, so you see, if it is a rectangular matrix, first the chances for it to have a unique solution. Hmm, yes. So what you do in such cases is you form the REF form. Okay. Uh, what you do is general approach. Now, not related to this question. Approach is first uh, find REF form of A. Okay. Or maybe you can say, maybe you can find the REF form of this augmented matrix of A and B. Now, in this augmented form, there are two possibilities. Okay, one possibility is, let's say I'm creating an array over here of order 3 cross 4. Here you have 1 0 0 something 0 1 0 something in 0 0 0, and I'm writing it as some constant. Okay, so the idea here is hmm, the idea here is if there are no zero rows in the REF form of A, then you get unique solution for the system Ax equal to B. Okay, means if the 0 0 0 is not here, then what will happen? This means the REF form here. Okay, I have taken a square matrix here, but since even still, if you take any non-square matrix, even if you take any matrix like this, in this case also, let's make it. hmm. So if there are no zero rows on this side, then it means it is going to have a unique solution. But here we see that there is a zero row. Okay, in fact, there are two zero rows. So the possibilities for it to have a unique solution is not there. Fine. But then two cases are left. Either it can have no solution or it can have infinitely many solutions. So you see how you decide. Let's suppose there is a row such that here all the coefficients are 0, but here on the right side you have some constant k. So there are two possibilities. If k is equal to 0, then there are infinitely many solutions for the system. Why? Because this would mean you have 0 times of x plus 0 times of y plus 0 times of z equal to 0. Now this is true for any value of x, y, and z, right? So from here, if you are getting any fixed value for x and y, like you got here, still this is true, right? Uh, hmm.
Okay.
Yes, sir.
But if your k is not equal to 0, then no solution. Why no solution? Because here what will happen is you can say it will mean 0 times of x plus 0 times of y plus 0 times of z equal to some k. Now this is not possible. All the coefficients are 0, then you cannot obtain any non-zero entity.
Okay. Got it.
Okay, fine. This will need some correction. Maybe just a second. This needs some correction. Instead of writing this, we should write it as if the number of pivots equal to number of columns. The number of pivots of A or row echelon form of A, same thing, are equal to number of columns of A, then the system AX equal to B has a unique solution. So we say this if A is full rank, then it has a unique solution. Okay, so I hope it is clear. Okay, how many pivots do we have here? One pivot is this, one pivot is this. So there were only two pivots, but there were three columns, one, two, three. That is why this particular system is not a case of unique solution. Fine. Yes, coming back to our original question, first option is done. Second says, consider a system of linear equation Ax equal to B. If B is a linear combination of the columns of coefficient matrix of A, then the system Ax equal to B has a unique solution. Now, this second point is wrong. Why? Because if B is a linear combination of columns of coefficient matrix A, then it means the system is consistent. Means the solution will exist, but it can either be a unique solution or it can be a case of infinitely many solution. That is why the second option will not be a correct answer here. Fine. Third says if A is an M cross N matrix such that M is less than N, M means the number of rows. The number of rows is less than the number of columns, then Ax equal to 0 has a unique solution. Now again, this is not true. Why? Because this would mean, see, N denotes how many variables you have. Okay, and M denotes how many equations you have. So let's suppose you have let's suppose you have uh, two equations and three variables. So in this case, there is no possibility of getting a unique solution because there will be a free variable always. What do we mean by free variable? The variable corresponding to the non-pivot column is what we call a free variable or an independent variable. So if there is an independent variable, that means either there is a no solution or you can substitute any value for the free variable and it is a case of infinitely many solution. Okay, so I hope this is clear. For this particular case, when you have more variables than the equations, you cannot have a unique solution. Fine.
Understood.
Hello. Second, uh, as we saw here, for a unique solution, A has to be a full rank matrix. Full rank matrix means the rank of the matrix should be equal to the number of columns. Number of columns here is n. So it says the rank of the matrix should be equal to n. But what we know about rank is always less than or equal to minimum of m comma n. Means whichever value of m and n is minimum, the rank cannot go beyond it. So here the minimum value is m, right? So the rank at max can be m. So if we are saying the rank at max can be m, then there is no possibility of the rank being equal to n because m is strictly less than n. This is one extra uh, maybe reason you can give why this option is not true. Okay. Any doubts?
No, sir.
Okay.
No,
If you're
sir. Yes.
writing your doubts in chats, then please unmute and speak because I can't see the chats as of now. Okay, the fourth one says if A, okay, the fact that I said, I'll just write it here so that you keep in mind. B, you can write it as a note that the rank of a matrix A of order m cross n is always less than or equal to minimum of m comma n. Okay. Fourth says that, sorry, that if A is an m cross n matrix such that rank of A equal to n, then it will have a unique solution. Yes. Fourth option is correct because rank of A means how many pivots you have. Okay. And if the pivots are equal to number of columns, it means you have n pivot columns, then the system will have a unique solution. So fourth option is correct. So if there are any doubts, you can ask. Hello.
Guys, please unmute if you have any doubts. You can unmute and ask your doubts. Else it will be a one-sided session. Uh, no point of having that. You can have that anywhere. You can watch the recorded videos. They will be one-sided. So please, if you have any doubts, ask them. If you don't have anything in mind, you are just like, I am totally oblivious. I don't even understand what is written on the screen. It's complete jargon to me. Say that as well, so that at least the Pancho has an idea of what he needs to explain. Else he will just assume that okay, people understand everything and we'll just move on with this. So if you want it to be worthwhile, it is your end term, guys. Right? It is not even quiz 1 and quiz 2. It is your end term. If you mess up here, it will stay. So and you don't even have a chance of improving, right? So just make it make it worthwhile for him as well. He's putting in the effort actually to explain it to you guys. Make it a little more interactive. So can we conclude rank must equal m for unique solution?
N.
Sabalsny asks that question.
A rank must equal to N. N is number of columns for the unique solution. Okay, yes, the simplest way of putting whether a system has a unique solution or not, rank must be equal to the number of columns. Hmm. Moving on to the next question. V is an inner product space. Now, what's an inner product space? What we learned about vector space, that we have two properties defined, property of addition and property of scalar multiplication. Now, if you add one more property of inner product, then the vector space becomes the inner product space. That means the inner product is defined on the space. Okay. And W be a space of V. W be a subspace of V.
Sir, I have
If V
totally
is
forgotten. Excuse me, sir.
Mhm.
I have totally forgotten addition and scalar multiplication I remember, but what is the property of inner product space?
uh, for it to be an inner product space, the inner product should be defined. So if they are not explicitly defining any new inner product from their side, then we assume they are talking about dot product. So by standard, we take dot product as the inner product. So if V is an inner product space, then it would mean for the vectors of the space V, the dot product is defined. That's it.
And one thing more I had a doubt about, sir. Whenever we are taught projections, we say a projection of vector on another vector, and we find out the dot product by dot b by mod of a and mod of b, right? Cost
Mhm.
inverse. But when we are given in exams, we get projection on a line, projection on a plane, and I cannot do that. How to do that?
Sure. We'll cover both the things in this question itself. Okay. Hmm. Basics lie in the same thing, that if you are taking a projection of a vector, you take the projection of one vector on another vector. That means what? I'll just draw something to explain, and that should cover most of the part for us. Not this. Say we draw something here. Okay. I have this vector v, and then I have this vector u. Okay. So if I say projection of v on u, what will it mean?
It will be
The
mean that
projection of v,
it will mean the end line will just perpendicular. Yes, that is the projection.
yeah, means I am talking about this guy. Okay. What's the length of this guy? So for the length of this projection is given by the dot product. Okay. So dot product of v and u will give me the length here. So v dot u will give me the length of this. But now what should be the direction? I will also have to mention the direction, right? Correct? Hello.
Yes, sir. Yes, sir.
This is just length. So this v dot u is just length of this projection. I will also have to mention the direction. So the direction is given by u cap. And what is this u cap? U cap is any unit vector in the direction of u. Okay. U cap here means unit vector on the direction of, in the direction of u.
Yes, sir.
Fine. This means I am taking u and I'm dividing u by the length of u. Okay, this norm, this symbol of norm here means I'm talking about the length of u. Okay, so
Okay.
if I want to find this length will be given by the dot product of v and u. Now this is some scalar quantity, just a number, right? So I'll have to give it a direction as well. The direction is u cap, and u cap is a unit vector along this direction of u, because this just gives me the length of the projection. If I, because projection is going to be some vector as well. So the length has to be given some direction, and the direction is given by the u cap, because this is the projection of v on u. That is why it is given by u divided by norm of u. I hope it is fine. Okay,
Yes.
just a second.
Yes, sir.
Hmm.
Sir, actually, the formula for that cos theta was v dot u by norm of u into norm of v. So I'm not seeing the norm of v in the denominator.
You are saying that it is norm of u by norm of v.
No,
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 there is no norm of.
v dot u by norm of v into norm of u. That is cos theta, no?
That is cos theta. That is a different thing.
Okay.
Cos theta is what? See, here it means if I say u dot v, it means it is norm of u times norm of v into what?
Cos theta.
Cos theta, right?
Mhm. Mhm.
So this is your dot product. How, what your dot product means? Okay, your dot product basically means the length of u times the length of v times the cos theta times the angle between them. If theta is this.
Okay.
Okay.
Yes.
Yes. Coming back to the question, what we were talking about the projections here. First says PV equal to V for some V in V, then V belongs to W. Now what we hear is if P is the projection of V on U. Okay. Now what does this mean? Can anyone explain? So we are given that V is a subspace of, sorry, W is a subspace of V. First point. Fine. The next point is P is the projection of V on W. Okay. So if we project our V on W, it is being represented by this linear operator P. So first says if PV equal to V for some V in this space, then V belongs to W. Okay. So here we were given that the projection is defined as this, that you take any vector from V, you apply the projection, and then the vector will reach or maybe will get transformed into some other vector that will lie on the subspace W. So here, this would mean what? This would mean for any V in your domain, for any V in your domain, the image of this vector, the image of this vector will be what? PV will lie where? In W. Now this is very general. Okay, as of now we are not even checking what's there in the option. It's very simple, right? You are given a function from a domain to some codomain. So you are saying that if you pick any vector, or maybe if you take, just think of it as a function. If you take any point from your domain and then you put it in your function, you take its image, then its image will lie in the codomain. This is what we have written over here, right? Any vector in domain gives you the image in codomain. This PV means the image. Once you apply the image means you apply the projection on this vector, or maybe you apply any transformation on this vector. Projection is also a kind of transformation. And this PV belongs to W. Okay. So here it says if PV is equal to V, then V belongs to W. So it is saying that PV itself is equal to V, right? We are given PV equal to V. Then it means what? Now instead of PV here, you can just substitute V and you will get what? This V belongs to W. Right? This is making sense. Now if you want to
So,
visualize it, how you
so V first belonged to the bigger vector space V. Then it suddenly changed to W just because the projection was there and the projection did not do anything. It just did the same. It was same, right? Like it kept the vector same, only the V. So it is in W, right?
hmm, I'll give you one way of visualizing it, and after that you won't get confused. Okay, just look at it. What projections do if you go to the fundamental level? Suppose this is my codomain. Let's say this is my W, the plane on which I want to take the projection. Fine. Or you can consider this entire space as my V. Fine. So what my projection operator does is, let's suppose there is some vector here. I'm calling it U. There is some vector here in the space V. So if I apply projection on U, this will mean I will take the shadow of U on my subspace W. Okay, this P of U will denote the projection of U on my subspace. Fine, we all know this, correct? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
But what happens? We are going to do the same thing again. But this time you say, let's
Okay,
say
now
I'm drawing.
this time you are saying that the vector itself lies in W and then there is no.
Yes. So if the vector itself will lie in W, okay, this is the vector. If the vector itself will lie in W, then the projection of V will be V itself, right? Makes sense?
Yes.
Hello.
Yes, sir. Then what is the option that they have told?
Right. So our point is that if I have any vector already lying in W, then P of V will give me V again. And the vice versa is also true. If P of V is giving me V again, then V must lie in W.
Sir, according to first option,
Mhm.
this means angle V is aligned to W, means angle between V and W is 0. So that cos
First
theta, V cos
option.
theta should be PV.
W, 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 W is not any vector. You can't uh, say that.
Okay,
But yes, it's a subspace. So it means if
okay,
your subspace will lie on W. For example, you take the floor of your home as W,
okay,
okay, and the entire room itself as V. So let's suppose I have any
okay.
stick
Uh,
that I am uh, holding it in my hand, let's say, okay, and it's slightly slanted. So what will happen? The shadow from the lights will fall on the surface. That is my W, right? And the shadow will be on W, that is on my ground, correct?
mm,
But what happens
mm.
if
That
the
is
stick
shadow is
itself is there
PV.
on the ground? Yes, yes. What happens if the stick itself is there on the ground? In that case, if stick is lying on the ground, then the shadow of the stick will be same as the stick, right? Hello, it makes sense, right? If this is your ground, this is your stick.
Yes, sir.
So there will be
Yes, sir.
no shadow. That means the vector itself is the shadow. That
Okay.
means there is no
Yeah.
project, there is projection. The projection is the vector itself. So if
Yeah.
the
Yeah.
projection is the vector itself, that means my stick is lying on the ground. My stick is already on, my vector is already present in
Yeah.
the space I'm talking
It's
about. The
WBM
space on
vector,
which I'm
then
taking the
angle should be
projection.
0.
Yes, the angle between the space W and my vector V is 0. Okay, and this brings us to a very important point. I'll go to the option third first. The important point here is the projection operator is idempotent. Now, idempotent means what? So let's say I'm writing here projection operator is idempotent. Now, this means what? This means that if P of V is equal to W, then P of W will remain W only. Okay. Or you may also think of it as, you might have seen idempotent matrices, right? P square is equal to P itself. And the idea is very simple. Let's suppose V is U is something. Okay. You take the projection of U, it becomes P of U. Now you again take the projection of P of U, but it will not change. It will still remain P of U only, right? Because now your P of U is lying on the subspace W. And what we saw here, if your vector is already lying on the subspace on which you are taking the projection, then after taking the projection, nothing will change. So
Sir,
PU,
this will occur always, sir. Whenever there is
yes,
a
always, always. So what we mean here is if you take projection of PU again, that means your P square U, it will still remain PU only. Right? Doesn't matter how many times you take projection now because the vector itself is lying on the floor. So it doesn't matter how many shadows you, always the shadow will be uh, what to say, overlapping with the vector itself. This
now by
option 3, I guess, is
yes,
also correct. Hmm?
So my question is, if I am given that the thing is idempotent, can I calculate the matrix anyhow, or just stay there?
No, you can't calculate the matrix if you're given it is if the matrix is idempotent. Because there are infinitely many possibilities for it now. P square equal to P. You just Google just Google idempotent matrix example. You'll get thousands of examples for the same thing. Okay. Now moving on to the option number two. Three we have seen. Now we will see option number two. So option number two says dimension of W is equal to dimension of this had a name dual of W, I guess. This W perp here means dual of W, or some may say the orthogonal complement to this subspace W. What is orthogonal complement? Orthogonal complement is the space perpendicular to this space. Okay, but this is not necessarily true. Why? For example, uh, if I'm talking about 3D, then your XY plane, let's suppose is your W. In 3D, your XY plane is your W. Then what will be your W perpendicular?
Z
Any
axis or
axis that is perpendicular to
XY
the
plane?
subspace W and also contains the origin. So that means the Z axis in this case is going to be W perp. And you see in this example, the dimension of W is 2 because it's XY plane. But the dimension of W, the dual of W is what is Z axis, and the dimension of Z axis is 1 because it's a line. Right? So option number 2 is incorrect.
Yes, sir. One more question, sir. Why do we always have to
Mhm.
consider that the origin is inside the W perpendicular? Why can't we consider anything else?
Because it's a subspace, and for subspace, it
Mhm.
must contain the origin.
Okay, means this is a
Subspace
rule or something.
definition.
Yeah, it's a definition. Affine spaces means we can
Yes,
choose.
when you might have learned about subspaces in yes, in affine spaces it is you can do, but in subspaces you might have read in week 3 that
Mm.
it must contain the origin. Okay, so that is why the only intersection point between the W perp and W is the origin. Okay, or maybe you can say origin must be there as a uh, must be there in the intersection of W and W perpendicular. Okay.
Sir, and this W perpendicular, is it the null space of the projection operator? Is it?
No.
Okay.
Yes, correct.
Okay.
Null space means the space such that if you apply the projection, you get zero
Yeah.
or you
So,
get the origin. So
okay.
if something is perpendicular to the space on which you are taking the projection, so perpendicular means the angle is zero. Angle is 90 degrees. So in that case, you're going to get your projection as zero.
Okay.
So yes, your W perpendicular serves as the null space or kernel. Okay, then this question, let's do it here only. It's a scalar value multivariable function of n greater than or equal to 2 such that the partial derivatives exists at all points and are continuous. You need to select the correct statements first. If the directional derivatives at x in all directions are 0, then x is a critical point of f. Is it correct? Yes, it is correct.
Yes, it is correct.
Why? Critical point means the gradient should be equal to 0, right? Either the gradient does not exist or the gradient should be equal to 0 or that point. And gradient is what? Gradient is just a vector that contains the directional derivatives for respective directions, right? For example, partial derivative and direction of partial derivative with respect to x is going to be the first component, second component will be partial derivative with respect to y, and so on. So if all the directional derivatives are zero, then it means the gradient is also going to be zero, and that is what gives you the critical point. Right. Uh, the second says the second order partial derivatives satisfy the relation uh,
Yes, that is
del
all.
square of f by del of xi and then del of xj equal to del square of f divided by del of xj and del of xi. This means basically if you want to take the double derivative or second order partial derivative, so it doesn't matter that first you take with x and then you take with y, it is same as you are taking first with y and then with x. Now, is it true?
Yes, sir,
So have you
because
heard about this
No.
Clairaut's
Claudet
theorem?
theorem.
Right, so this has to be given someone over here. So just refer to it. What was the spelling? It was, I guess, like uh, Clairaut's, no, Clai. Okay, no issues. Even if it is not present here, it's Clairaut's theorem. So what Clairaut's theorem states? Does anyone of you remember?
It states that if the function is continuous, then in any order you take the derivatives, they are going to be same.
Uh, Sorry, yes. Where were we?
Actually, I said that
Hmm.
Clauset's theorem, the theorem states
Mhm.
that if the function is continuous everywhere, no matter in whatever way you take up the derivatives, it is going to be the same.
Okay, fine, partially correct. Uh, it states that if the function is derivative for the first order, for the second order as well, then no matter in what sequence you are taking the second order derivative, it is going to be same. Okay, so here we are given that for the first order, the derivatives exist and are continuous, but we are not given the guarantee for the second order. Okay, so for the second order, if the derivatives are not continuous, then we cannot apply Clairaut's theorem here. Okay, so if I'll just open this statement. Okay, if it's mixed, second partial derivatives are continuous. Okay, so keep this thing in mind. This is very important. Many people fall for this trap. Here you are given that only the partial derivatives, the first order partial derivatives are continuous. You are not given the same for the second order partial derivatives. Okay, but the theorem states that it has to be done for the second partial derivatives. The continuity should be there for the second partial derivative. That is why you cannot apply the theorem here, and this statement is wrong. Fine. What about the third guy? Third guy says the ith component of the gradient is the partial derivative of f with respect to the ith variable.
Yes,
Again, basics. Fourth one says if there exists a unit direction u such that the directional derivative of f at that point in the direction of sorry, it says for each point there exists a unit direction u such that the directional derivative of f at that point in the direction u is zero. Now what about this? Now this is again very simple. How for that we'll look at uh, this. So if I have to calculate the directional derivative of f the directional derivatives,
Sir, your voice
directional
is
derivative in the direction of
breaking.
u for a comma b. Okay. Maybe there could be some internet issues. It will get fine. How do you get that gradient symbol here? Do we have it? No worries. So you might have seen
Right, that's
this. I'm
Nabla,
just
right?
writing it this. Oh, yeah, thank you. Yes. So if you just take this gradient at a comma b and then you take its dot product with the unit vector u. Okay, let me call it the unit vector u. So dot product of the gradient of f at the point a comma b and you take its unit, you take its dot product with u, that gives you the directional derivatives of a point a comma b at some point u. Now what this means is, what is this? F of a comma b is this sorry, this gradient f a comma b at some point a comma b Hello. Sorry for that. Yes. So it says that it could be zero for any given point. Yes, it is true. Because why? Because the gradient could be zero for any such point. Okay. So if gradient could be zero, then this thing can also be zero, or this dot product itself can become zero. So it is true for, what was the question? The question was, for each point there exists a unit direction u such that the directional derivative of f at that point in the direction u is zero. Yes.
So
Okay.
when
Or
does such a point exist? When the
even
gradient cannot be zero or something like that.
even even here you can say that it is eventually a dot product, right? So it says there should exist a direction such that this entity is zero. So what if this gradient will be a vector? I just need to pick any unit vector that is perpendicular to this vector and I will get this as zero, because this is eventually a dot product. You just take anything such that anything that is perpendicular to this and I will get this dot product as zero. So I can always get a unit direction u. Okay. And that unit direction u will be perpendicular to my gradient. If someone asks you that what should be your u cap, you can say it has to be perpendicular to the gradient. Was that your doubt?
No, actually, I was thinking that this is quite a general statement. So where can such a thing be there that gradient won't be zero at all, no matter what happens?
Yes, gradient could not be zero. Totally
Okay,
agreed.
okay.
But you can pick your u such that it is perpendicular to gradient. Gradient will be a vector, right? So you can
Yes.
pick a vector that is perpendicular to it, and because it is giving you the freedom to choose your u. So you can choose your u in the direction that is perpendicular to the direction of your gradient, and then your dot product will be zero. And dot product is zero, that means the directional derivative towards that direction is zero. Okay.
Sir, the question I asked previously, the projection on a plane and a projection on a line, how to do that?
There will be questions here in the problem itself. Here you see this on a line. So we'll just get there. Won't take much time. Here, won't waste our time here. What can you do? Just take 3 out from the first row. This will become A1 minus of 2B1 and then C1. And then take minus 2 out as well. So 3 times of minus 2 times this will eventually become A if you do these operations. And determinant of A is 5. So 3 into minus 2 is minus 6 into 5 is minus 30. This should be the answer. Yes. Okay. Here, determinant of the matrix A6, A power 6 minus A power 5. Just try to
Sorry
calculate the
to
powers of n.
sorry to
Maybe you will
interrupt.
find any pattern here.
So, the previous sum
Uh-huh.
just show me, but so it's quick, it's fast. So what determinant of B?
Hmm.
So how it is calculated quickly?
See, first you take, if you are given determinant of B, so you can take 3 out from the first row. So it will
Oh,
become 3 times of determinant of a matrix as that the first row is divided by 3. So
okay.
it will be A1 minus of 2B1 and then C1. Fine when you take 3 out from the first.
Yes, yes, yes.
And
Yeah.
what you do is you take minus 2 out from the second column. So
Okay.
that becomes 3 times of minus 2. If you look carefully, you're left with only the matrix A.
Okay. Okay.
So it is 3 times of minus 2 times determinant of A, which is 5,
Minus six.
equals minus
Minus
30.
six into five minus 30. Okay, got it. Thank you.
Yeah. Yes, start looking out for the pattern here. A2, what will be A2? A power 2. Just quickly write it somewhere. What was our A? 7343. What will be A square? It should be this times this again. What it will be? 49 plus 12, 51, 61. Then 21 plus 9, 30. Then 28 plus 12, 30, 40. Then 12 plus 9, 21. Is it?
Yes, sir.
Okay. What is A cube then? Times of
Sir, is there an easier method, or we have to keep on like a cube into a squared and a cubed into a squared into
mostly they will find a pattern here. Most probably, if we will not find a pattern in the third iteration, we'll definitely try to look for a more smarter approach. Let's see what happens. 61 plus into 7 plus 30 into 4. Hmm, not smart, right? Yes, not a smart
517.
problem. That is fine. That is 817.
Sir, can we
But
do
is there any
a,
easy way of finding this determinant?
a to the
You
power
take
6? A to the power 6 is equal to a to the power 5 into a. So a to the power 5 takes common a minus 1. Can we do like that?
yeah, still we have a to the power 5
But
that needs to be
still,
calculated. Mhm. A to the power 5. Okay, maybe we'll not have to do much if we just keep doing it. A power 6 minus a power 5. Hope no calculation mistakes are made here. 49 plus 12, 21 plus 9,
or maybe
28 plus
C
12.
equal to like that, maybe printing issue.
Oh, I guess we should do it. We should do it. 7 and how much? 427 plus 120. Next is 183 plus 90.
I
Then you
have
have
calculated
28. Uh-huh.
273.
Okay, I'll just one more step and we'll do it. Okay. 120 plus 63. Yes. What was it? Could you repeat, please?
547
547
273
2. Okay.
364
364
183 183.
183. Okay. Uh,
Yeah.
what I am thinking here is just let's try to do one thing. Let's try to calculate what a minus I here is. A minus I here gives us
Actually, that
6,
determinants becomes 0.
3, yeah, 4, 2,
Mm.
and determinant of a minus I gives us 12 minus 12 equal to 0. Yes. So we need not to do all these things. So once you know that you are not able to observe any pattern, just quickly move out from there because otherwise you're wasting your time. There has to be any other way of doing it. Hmm. So either you get some pattern, or if no pattern is there, then it means you'll have to think about any other approach. So what we are thinking here, we were given what? A to the power 6 minus a to the power 5. So what we have done here is let's take k to the power 5 is common. We are left with a minus of I. Okay. Now we have to find determinant of this entity. So this is equal to determinant
0.
of a to the power 5 into determinant of this. So we do not care what determinant of a to the power 5 is because this entity here is 0. Okay. 5, 0 gives us 0. Easy.
Sir, one more question about here. A to the power minus 1, if I have to get, what is a smart way to do it?
Uh, okay. If it's a 2 cross 2 matrix,
Then it is still okay. 3 cos 3 I'm talking about.
if it's a 3 cross 3 matrix, then you do this uh, Gaussian elimination and do it. For example, I'll take a very simple one. Oh, let's say here you're writing 6, 3, 6. Hmm. 1, 0, 1. Hmm. See, this is the matrix, let's suppose. Hmm. Let's suppose this is the matrix and you have to find A inverse. What you'll do in this case? The idea is you put your matrix here like this, and on the right hand side you put your identity matrix. Okay, you create this augmented matrix. On left part you have your identity matrix, and right part you have your
So your voice is not audible.
Sir, your voice is lacking.
yes. So I was saying that you just perform the elementary row operation on both the sides, keeping in mind that our task is to make this as the identity matrix, this side, left side as the identity matrix. So yes, we perform this operation and this has now become this. So we got what? We got 1, 0, minus 1 over here. Okay, now it means if this has become the identity matrix, then what I have left on the right part is the A inverse. So if someone asks me about the A inverse, I can simply say it is this. Okay, so I took the A inverse of this matrix and I took the identity matrix of this matrix. So this is what I have.
Sir, your voice is not audible at all.
Guys, I think the country is having some network issue. Please bear with him. He'll maybe change his network. And the country, your voice is breaking a bit. Your network is unstable.
Yes, I just refreshed it. Now it should work fine. Hmm. Now we are on, oh, just one more problem here. A square is 2i, b square is 3i, determinant of a less than 0, determinant of b greater than 0, determinant of a b. Simple. Just take determinant on both sides. Determinant of a square becomes determinant of 2i. You take 2 out, it becomes 2 to the power 4 because it's a matrix of order 4. 2 to the power 4 is 16. So square of determinant of a is 16. So determinant of A is either going to be plus 4 or minus 4 given that determinant is less than 0, then determinant of A becomes minus 4. Okay, you do similar thing with B. Given B is greater than 0, you get B equal to 9.
Sir, I could not
So minus 4 into
understand
9
this.
gives,
Sir,
I could.
not able
okay,
to understand. Can you write and
sure, sure. Uh, but you just stick to the calculations of determinant by taking determinant on both sides. Okay, let's do it. You see, I'm given this. I can take determinant on both sides, and this will become determinant of a square equal to determinant of 2i. Now this I is a 4 cross 4 matrix, right? So if I take 2 out from here, this becomes what? This becomes 2 to the power 4 into determinant of I. Determinant of I is going to be what? 1 only. But I'm still left with 16 here. So a square is equal to 16, and there are two possible answers for determinant of a, which are plus minus 4. But we are given what? the determinant of A is less than 0. It is given in the question itself. Thus, only possibility here is determinant of A is equal to -4. Okay. Can you do the same with B square equal to 3i?
Yes, sir.
Just repeat all the steps. You will get B equal to 9. 9 into
Yes.
-4 will give you -36. Now, the question that someone asked, that A comma B
So,
is the projection of a
sorry to
vector on
interrupt.
the line.
The earlier one, could you please explain, because I'm not able to understand. So what you did, but
This
in
one.
above also you made some, you something, you annotated something, that one. Yeah. Yeah. So that
This.
one, what is this? Yeah. So
Oh, this is, let's suppose you're given a matrix and you need to find the inverse of the matrix. So what
okay,
we do is you create this augmented matrix. Let me write it as,
with the high identity matrix. Okay. Then
hmm, okay. Your task is what? Our task is to perform the row operations only,
okay.
such that the left side becomes I,
So R1
and
minus
let's
R3.
say my right side will become something B.
Okay.
Okay. Operations needs to be done in a way with the target that I need to make my AS identity matrix. The
Hmm.
same operations will be done on I as well. That will give me some matrix B,
Okay.
right? Now this B matrix is going to be the inverse of my A. Okay. And that is why you first need to check whether the determinant of A is non-zero or not. Because if the determinant of A is 0, then you can't make identity matrix out of it.
How the B inverse came here?
This is basically on A, you need to perform the operation such that you get I. The same operations when performed on I will give you some matrix. Let's call it B. Okay.
Hmm.
This B is what your A inverse is.
Hmm.
Okay.
Okay.
For example, here I had identity matrix here, the given matrix here. Now I need to
Okay.
perform the operation such that this matrix becomes the identity matrix. So what I did, I
Hmm.
performed this operation. So the operation that I'm performing on the left hand side, the same operation, that is from the row 1, I'm subtracting row 3.
Hmm.
I'll do the same operation on right part as well. This will give me this, right?
Okay.
Now, since I have got identity matrix on the left part, I will stop.
Hmm.
And this matrix over here is what I can call my inverse of A. You see this guy and this guy.
Yes.
Okay,
So
so
this
is
method is
this an
also valid
easier
for
way of
4 by
finding
4
the,
and 5 by 5.
yes, works for any matrix, okay, by Gaussian elimination or Gaussian reduction. You do this, try to find the inverse of the matrix. Hmm. This was the problem we were talking about. If A comma B is the projection of vector on the line
No,
using
no, the next,
standard inner product.
sorry to interrupt. That next
Yes.
one, the next sum how you did is A squared is equal to 2 of 2 into identity matrix. So I 4. So
Identity matrix of order 4 cross 4 because here it is given, right? You take
okay.
determinant on both sides. So you take any constant. If you try to pull any constant,
Outside is okay. It will come the power. Okay. Then
multiply it. Sorry, you have to put the exponent as the order of the matrix. Order of the matrix is 4. That's why it became 2 power 4.
okay. Okay. Got it.
Now this is equal to 1 and this gives you 16.
Okay.
Rest calculations are easy.
Got it. Got it.
Hmm.
Thank you.
Now if we come to the question A comma B being the projection of vector on the line y equal to 2x using the standard inner product find A plus B. So what you have learned so far, you learned how to take the projection of a vector on another vector. Now you think that this line itself is a vector. So if I talk about y equal to 2x, which vector I'm talking about? Okay, so this also can be seen very easily. Okay, this y equal to 2x is my vector 1 comma 2, right? Why it is my vector 1 comma 2? Because you notice if I put my x as 1, the y becomes 2. Okay, so I need to keep track of the direction. Okay, it doesn't matter what the vector I'm getting, I just need to get a vector in the direction of this line. So rather taking a vector, the best solution is to take the unit vector. Okay, and perform all the operations on unit vector. Okay. So unit vector will be this divided by its length. So length here is square root of 5. Okay,
So why?
can we
So
show that case?
why did you take the unit vector?
Because I just need the direction of the line.
Okay. So
Okay,
in case if I did not take the unit,
yes, whenever dealing with the projections, just take the unit vectors of the plane in which you are taking the projection on the of the plane or of the line on which you are taking the projection. Forget about the formulas. Do not use any formula. Just take the unit vector. Rest everything will be done for you.
answer one more question.
Okay.
If it was y is equal to 2x plus 3, say, so I would have taken the something other, right? Like x is equal to 1, y is equal to 5, or something like that, right?
Yes, but it won't be a subspace. It won't be a subspace that will pass through your
Yeah.
what? It won't be a subspace that will pass through your origin.
So if such a question is asked in
Right?
the exam, then how to go about doing it? First, you solve
Won't
this.
be because it's not a subspace for you.
Okay.
We are only dealing with the subspaces. So if
Okay.
it does not pass through origin, it's not a subspace. Make sense? Right. So even they give you the plane in which you have to take the projection. The plane must pass through the origin. Okay. Yes. So if we make some drawings here, she will plot function. We were saying is we are given this y equal to 2x, this line. And what we did was we took a vector. Okay. Uh, and what was our vector? Our vector was 1 comma 2. So you see both means the same thing. So this is just a vector pointing towards the direction of y equal to x. Okay. And we need to take the projection of what was it? 3 comma 1 on it. So as we discussed here, okay, we'll only be dealing with just hmm. So as we discussed here, if this is my v and I need to what if this is my v and I need to calculate this projection, then what I'll do is I'll take the dot product of u v with the unit vector in the direction of u, and then I'll multiply it with the unit vector u. Okay, what it will give me? Yeah, again, no need to memorize any formula. We can see that why it's happening. So the projection of u on my line, let's call it L, nothing, just dot product of u and v hat, and then in the direction of v hat. Sorry. Okay, so what was my u? Uh, it is given in the question 3 comma 1. So 3 comma 1, you take its dot product with what you have calculated over here, and then uh, this. This will give you what? 3 times of 1 is 3 plus 5, 5 divided by root 5, and then root 5 here is just 1 comma 2. Okay, a plus b is 1 plus 2, 3. Simple. Hello.
Yes.
Yes, sir. Yes, sir. It is
Okay.
clear.
Now what happens? Let's say this was just a line, right? What happens if I ask you to have the projection of this vector on a plane? Okay. Let's say I ask you the projection on a plane S. Now, what you do this again, like said, this entire line could be represented by its basis unit vector. Okay, everything comes down to basis. Okay, so if I am given this L equal to y equal to 2x, then I can write my n as span of v cap, right? Span of this vector will give me this line. So similarly, if I'm given any space, okay, that space could be written as a span of some vectors.
So,
Okay, let's say the
just a
given
question.
vectors are
Just a
Mhm.
question. The question is, the span would be 1/√5 comma 0, and then 0 comma 2/√5 for this case. No.
no, just this much.
Okay.
Even see, even if you write span of 1 comma 2, that means the same thing. Multiply
By any
anything to this
square.
span, it remains the same thing, right? But this cap is necessary while doing this multiplication. Okay, because we do not want the length of the vector that we have chosen here to affect the length of the projection. That is why we pick the unit vector. We just need to keep the count of the direction. Okay. Same goes here as well. So if I give you the space or any plane, okay, any plane or any hyperplane, let's say, okay, so this is not just a plane, you can call it hyperplane because it's in 3D. It's not just a plane, it is a three-dimensional space. Okay. So my point is here, we are going to do the same thing, but let's suppose we couldn't have done this with just 1 comma 2. We had to perform some normalization here, right? So here also we can't directly go with the given span. What we have to do is we have to find the orthonormal basis. We can't go with any basis. We have to find the orthonormal basis. Let's say this W1, W2, W3 is the orthonormal basis. How do you find the orthonormal basis if you are given something like this? Use this
Cosmic process. Gram.
Gram-Smith orthonormalization. Okay, I hope you know what this means. If you need basics on it, that how to perform Gram-Smith orthonormalization, is there any way that we will not have to memorize how to do it? I'll also show you it in a second. But first, let's suppose you performed Gram-Smith orthonormalization and you got this basis. Okay. this orthonormalized basis. Then the projection is very simple. Projection of U on S, right? So let's suppose when we were just talking about a single what? We were just talking about a single line. What we did? We did, you just take your V cap, you take a dot product of U, then you take the direction of V cap. That is, it is what we did, right? For a case of single line. No, no, this is what? This is, you have broken down your space into three perpendicular axes. So instead of V caps, we will use W1. So take the dot product of W1 with U, and then this one is in the direction of W1. Now, the same thing you can do in the direction of W2 as well. Because you have broken down your space into three directions, W1, W2, W3. Now all three dimensions, because are perpendicular to each other, I can directly add them. Right? If the vectors are perpendicular, I can add them like this. And that is why making it orthogonal first is important, because if it is orthogonal, I can add it like this. And orthonormal, because I do not want the length of these vectors to hinder what I will get as a projection. So that is why we perform normalization. And orthogonal, because
In
once it is done, I
in
can
this
just
there
add it
is
like
no unit vector.
hmm?
In this there is no unit vector W1, W2, W3. We have to take
Could you
unit
repeat,
vector
please?
of W1, W. We have to take the unit vector of W1,
No, no,
W2,
no.
and W3.
W1, W2, W3 itself is a unit vector. It's an orthonormal basis.
Okay.
Orthonormal means what? All three of them are unit vector and are perpendicular to each other. Okay, so all three of them itself are unit vectors. Okay, so if the examiner is in a good mood, it will just give you a basis that is already orthonormalized. You just do this. But if he or she is in the bad mood, they'll give you random vectors, a random basis, and you'll have to perform the entire Gram-Smith orthonormalization to get a orthonormal basis. Yes. Again, we'll just do maybe the last topic that would be important for you here, what this Gram-Smith orthonormalization is. Again, the idea of the Gram-Smith orthonormalization is that I want to make the vectors perpendicular to each other. Okay, so let's suppose I'm given this vector v. Okay, and this is my vector u, and my unit vector is u cap. So what is projection here? We talked about projection, right? This projection we said is this projection vector is what? Dot product of u, dot product of v with u cap, and then you multiply it with u cap because it's in the direction of u. So this gives you the length. The first part gives you the length, and the second part gives you the direction. So let's suppose I have u cap as one of the basis vectors. If I have to find the second basis vector, that will be perpendicular to u. Okay, this guy. Let's call it b. I need to find this b. So if you know the triangle law for the vectors, that will say If you add this and B, this will give you V. Correct? V is equal to this entity dot U cap times of U cap plus B. So from here you get your B as V minus of this guy. Hello, is it audible? Sorry, am I audible or any doubts here?
No doubts.
Yes,
No,
you're
sir.
good.
Okay,
Sir, how can we relate this with Pythagoras theorem? Can we relate or not?
Pythagoras theorem talks about the length. So even if you check the length of V square, it will be equal to B square plus this guy's square. But
Yeah.
here we are dealing with vectors, not just the length. The directions are also involved. So that is why Pythagoras theorem will not do the work for us. Hmm. Yes. So our point is, if I am given, if I'm given a basis u1, u2, u3, let's say. So, and orthonormal basis, how will I find? I will start from, let's say my v1 is, see, to find the first vector, it's very easy. You just pick the first guy from here. It will be some base, it will be some vector. You just normalize it. Normalize it means you just take the u1 cap. Easy, right? You may find it written like this. You have u1 here, here you divide by norm of u1. So however you want to look at it, just think of it as a unit vector in the direction of u1. Fine. Hello. Doubts?
No doubts.
No, sir, clear.
Now considering this v1 is my reference, I need to find the second vector such that it is perpendicular to v1. Okay. So what I will do, I'll find a vector that is perpendicular to v1. I'm calling it my w2. Why not v2? Because v1 has to be this v2 will be an unit vector, right? So first, why should I worry about the length? First, I should worry about the direction, the vector itself. Later, I'll take a unit vector. So how do I calculate the w2? See, I'm given a vector v, I'm given a vector u. I need to find a vector that is perpendicular to e, perpendicular to u, right? I need to find the vector, the vector formed by v such that it is perpendicular to u, or maybe you can say the component of v that is perpendicular to u. So what I did v minus of this guy minus of this guy. Okay, and this was what? This was the projection along u. So what I did here, v1 minus projection of v1 along u1. Okay, projection of v1 along, sorry, v2. We are doing it for the v2, not v1. What was it? Projection of v2 along v1. So this is this v2 dot of v1 along v1. So this will be in direction of v1. Okay, that would mean your V2 is okay, just unit vector in the direction of W2, or you may find it written like this. Okay, first component, second component. Any questions? Hello.
No question, sir. We understood the process.
Now for the third one, it's simple. You just have to copy paste it, but have to keep track of all the previous components. So for example, here, if I'm doing for W3, I will say from V3, subtract the component of V3 along V1, then the component of V3 along V2. Okay, so let's first subtract the component of V3 along V2 right? And then subtract component of V3 along V1. Fine, and then you take the norm of it to get your V3. Now you can do this for any k. So if you keep doing this, you get for any k, what we need to do is we start with vk, means the component we were talking about, and we first subtract the k minus 1, its component along k minus 1, then its component along k minus 2, till its component along 1. So it will look like this: k minus 1 times, sorry, component of vk along vk minus 1. Oh, just a second. We took u2, u3. Hey, 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 hey. This is u3. Hey, this is u2. Okay, this is uk. Hmm. And you keep doing this unless you reach here. Okay, and then your pk is just going to be wk divided by norm of wk. Are there any questions? If yes, please ask.
Sir, I had seen a PDF you have just showing the contents with IIT Madras, multivariable calculus or something. Is there any PDF as
Hmm.
such? Would you please put it on the chat or something so that I can download it? The PDF you were showing, the contents, there was something like that.
In the chat, ping. It mostly these are the things. Maybe if you practice more, you will get a better idea. Okay, so even all the syllabus of M2, you need not to memorize anything. Just know the crux of what is happening. Okay, be it your fundamental spaces, what each fundamental space means, even what's the application of inner product, why I take the dot product. If you know this, your half of the work would be done. You will understand how the projections work if you just know why you take the dot product and how you take the dot product. And that would mean you have concluded your entire linear algebra. Just have the basic idea of transformation, what transformation does. For that, you should have a good idea of matrix multiplication, the different forms of matrix multiplication. That is, if I'm taking a transformation, it means that it is just the linear combination of the columns of the coefficient matrix, or maybe the columns of the matrix representation of the transformation. Okay, so just have the idea of what happens when you perform an operation and why you want to do it, then most of the things will happen automatically. Yeah, you do not have to memorize any formula. Yeah, that's all. I guess
Sir,
you
how to
understood very good.
sir, how to download
Uh-huh.
this? This is not downloading this multivariable calculus.
Because it's a page. It's hosted live. Uh, just a second, I'll see if it is present somewhere else. I'll share the PDF and you'll get from Chetanji. Okay, I'll share with him. Yes, any specific doubts you want to ask? Hello.
Guys, if you have any questions, please ask right now.
Sir, actually, the point where the steepest ascent, steepest descent I can get, but the point of no difference, that is the perpendicular one, that I cannot get in many tables.
Okay,
And one more
just a
difficulty.
second.
Okay.
Hmm.
And one more difficulty is that x cube y is equal to x cube at 0 point. Is it a saddle point or is it not a saddle point? Or in one variable calculus, the thought of saddle point is not there. Only saddle point comes in two variable or multivariable calculus.
No, in zero variable, sorry, in a single variable function also, we have saddle points. Sorry, just a second. We call it point of inflection. So zero for the function fx equal to x cube is a point of inflection
How is
wherein
it?
it
How is it?
is neither minima.
How is it different from a saddle point?
Mhm.
How is it different from a saddle point?
Uh, I'll have to see exactly what saddle point was. Is it same as point of inflection? Means what term was being used here in the lectures?
In the lectures, see, I am doing maths 2 now, that
Suppose
is, and maths 1 I had
not,
done quantum
yes,
of.
it is same as point of inflection.
Okay,
Okay.
now one thing more, the PDF that you shared with Mr. Chetan, actually, sir, Chetan sir, how
Here,
to
here
get
in the chat, here in the chat.
it is
Check chat.
okay.
Check this.
Where is it? Oh, mm, this is also not downloadable. Where is
This should be downloadable.
okay? Just a second, let it download. Okay, thank you. This is downloaded.
Hmm.
Hmm. Yes.
What was your question?
Yeah, how to find those points in which the curve is flat, that is, it is a perpendicular.
Perpendicular. How do you find perpendicular?
I
You're
mean,
given a vector and you need to find perpendicular to the vector.
No, no, no. That is not the
How?
thing. It is nearly the same thing. The gradient is given, the direction of
Mhm.
steepest ascent and the steepest descent I get. Now the point is that I have to find the thing in which it is level, that is zero, right? So how do I go
Hmm.
about doing it? That is
Just
a
take any arbitrary vector x comma y comma z,
okay.
okay,
Hmm.
and take its, or maybe u1 comma u2 comma u3,
Hmm.
and take the dot product of gradient and this guy, your
Hmm.
arbitrary vector, and equate it to zero, and you'll obtain an equation x comma y
Yeah.
comma z.
Yes, but the equation that we'll get will have more variables than the number of equations. So there will be so many. So actually, that means that there are so many
That would
vectors.
be a space.
Yeah,
That would
yeah.
be a space, vector space.
And exactly, can we explain the notion of closed and bounded domain?
Just a second. Yes, what was it?
What do you actually mean by closed and bounded domain? Means closed
Uh,
domain, open domain. What do you mean by at the boundary? Means what is the actually meaning of that?
Meaning, if you say, for example, I give you a circle, right? So
Okay,
if you're only allowed to stay inside the circle, you can't be on the circumference of the circle, or you can't be on the perimeter of the circle.
okay.
Then you say it's an open boundary, right? But if you're allowed to be on the perimeter of circle as well,
Hmm.
then we say it's a closed boundary. So you know the exact point where you need to stop, or
Okay.
where you can be there. So if an open boundary, if someone has to ask me that, let's suppose this x can't exceed 2,
Hmm.
what could be the maximum number this x can get
If,
on this direction? I
what
know
was
it's
the?
very close to 2, but it's not true 2.
Hmm, hmm, hmm.
But if it's a closed bounded, I know that I can get to 2, and 2 is the maximum, the exact point I know where I can get.
Got it. Thank you.
Any other questions?
Guys, any other questions? Anyone? If not, shall we wrap it up? Tapanshu, are you there?
We can wrap it up.
Sure.
Okay, so I'll just
Can I get the section of first practice session on YouTube channel of Kaziranga?
uh, pardon. What do you need?
Can I get the first? This is revision two or part two revision session?
This is the first revision session for the maths 2.
Okay, okay, okay.
Yeah. So everything that was discussed here, you can get that by mailing us. I'll just put in the 3 email IDs. Just give me a second.
Mock test also will be discussed.
Just a second. See, we have sessions for other courses as well, but for maths 2, we had only planned this session. So just for the revision session, we had not planned any mock test discussion sessions or anything, because usually that takes some time, and right now you're all short on time. So we just wanted you to understand the main topics first, and the rest, once you understand those topics, you can do the questions on your own as well. So we wanted to focus on what was absolutely necessary, because we are very short on time. It's August
Yeah.
25th and August 31st is the end term itself, right? So, so these are the three email IDs. You can copy these, whatever you require from the session. Maybe you need slides, or maybe you need some drive link that was shared in the session, right? Anything that was shared, you just mail to these email IDs, and you can get those. Regarding the recording, it will be available on YouTube. And as I've already mentioned, we have planned for more such sessions for other courses as well. Uh, we will be only discussing the things that are absolutely necessary for the end term. We will not be focusing on other things as of right now, since we are very short on time. Okay, so thank you all for joining today, and I hope to see all of you in the future sessions. And most importantly, thank you so much, Dipanshu, for taking this session, taking time out during the end term week. Thank you so
Hey,
much.
cool.
Yeah, thank you.
Cool.
This is really amazing and really very helpful actually. So I think it's a very slow manner is covered. The clearly explained the Karthi also. It's very interesting. So like this, maybe you can arrange at some other sessions also. Maybe it will be useful for
Surely,
us.
surely,
Thank you.
surely. We have already planned those out, and we have sent an email today at 6 o'clock. So you can take a look at that, and we have shared every detail for the future sessions as well. So, and yeah, I
Thank you.
agree with you. Dipanshu has a knack of explaining things really well. So
Thank you. Thank you.
just stop the recording now. Just give me a
Thank
second.
you.
Okay, perfect. So now it is, now that it has stopped. I was actually quite